I'm Bhanu Pant from Indian Institute of Technology, Jodhpur, India. First, I would like to thank the organizers to provide me the opportunity to talk here. So today I'm going to talk about the Corsica simulation for massive quarks in hadronic showers. Okay, so first I would like to take this opportunity to talk a little bit about this experiment, which is called GRAPE-3 experiment, which stands for the gamma ray astronomy at PV energies phase 3. It's basically a ground-based detector located at Ooty, Tamil Nadu, India, in the southern part of India, at an altitude of 2,200 meters. It's an Indian-Japanese collaboration with nearly 20 institutions. So we have 400 plastic scintillator detectors spread over 25,000 square meters of area. And we have the energy sensitivity in the TeV to PeV ranges. And you can see in the inset, the first inset, which is the GRAPE-3 muon telescope, it's basically 4 stations. These are 4 stations covering 560 meters square of area. And these 4 stations contain 4 modules. And in each module, we have 4 layers of PRCs. So here you can see inside the view inside this module, and we have these 4 layers of PRCs, and they are orthogonally placed to each other. And since in each layer, we have 58 PRCs. So in total, we have combining all this with 3,712 PRCs, which act as a muon detector. And each PRC is 6 meter by 6 meter by 0.1 meter in cross area volume. So the energy threshold for this muon detector is basically 1 sec theta GeV. So basically, if you have a vertical muon, basically you will get energy threshold of 1 GeV. Only those will pass through this detector. And since I'm working in this collaboration actively and currently working in this area, my actual work is on the diffuse emission of the gamma rays. And in that, I study 2 components. First, the extragalactic background, which arises from the ultra high energy cosmic rays interacting with the gamma CMB. And the second is the galactic background, which comes from the cosmic rays interacting with the matter and radiation of the galactic view. So that's the end of the advertisement. Now moving on to today's talk. So let me just first talk about what is an extensive ray shower. An extensive ray shower, basically when a primary cosmic ray comes in, it interacts with the air nuclei and produces a secondary cascades. So basically we have pions, kaons, and some other nucleuses are there. The pions and kaons, they again decays, pion decays to muons, again kaons decays, and the muons again decays to electrons and neutrinos, and we have a huge cascade of secondary particles at the ground. So just to get an idea, if you have a proton primary at 10 to the power 15 electron volt, then at the ground you'll have roughly 10 to the power 6 secondaries, and in which 80% are photons, 18% are electrons or positrons, 1.7% are muons, and 0.3% are hadrons. Okay. Now, you know that mostly these secondaries are pions and kaons, but if we have a high energy cosmic rays comes in, it might be possible that some of the charm particles are also produced in that huge zoo. But even if they get produced in that zoo, the production is very low. It's around 1 or 2 charm hadrons are produced in a single proton nucleus collision, if at considering the lab energies of 10 to the power 18 electron volt. So why care about these charm particles if it's so low production rate? But even if their rate of production is very low, the charm particles are produced at an energy of PeV ranges. And these PeV charm particles produce as muons in the TeV 100 and TeV ranges. So these muons and neutrinos, since these are atmospheric muons and atmospheric neutrinos, they will act as a background. So the study of these backgrounds is very important when we study in the case of neutrinos from the astrophysical sources. So as an example, I'm taking one particular D as an example. The D plus goes to K0 bar mu plus nu mu with 7% branching ratio, and D0 goes to K minus mu plus nu mu, 3.2% branching ratio. So we have from the charm D meson decay muons and neutrinos coming out in the 100 TeV and above 100 TeV ranges. So, and these muons are expected to be observed at the ground. Okay, so how to do it? I mean, how to get an idea about this charm muons and neutrinos arising from the charm decay. So we used a package called CORSIKA, which stands for Cosmic Ray Simulation for Cascade. It was basically a Monte Carlo program, which was first developed in 1989 to perform the simulation for the cascade experiment. It allows simulation of decay and interaction of particles up to 10 to the power 20 electron volts. And the thing is that it provides energy, location, direction, and arrival time, all the secondary particles that arrives at the detector level or at the observation level. And it also includes several hadronic interaction models. Some of the models I've just written: QGIS Jet, Sybil Fluka. And the electromagnetic interactions are taken care by the NKG, which is a function. If you have heard of Nishimura Kamata Grayson function, and other is the EGS4, which is electron gamma showers version 4. Okay, so these are the simulation parameters. I used Corsica version 7.7410. The hadronic interaction model is Sybil 2.3, and Gaisha is the low energy interaction model. So if we have energy of like 80 GeV in the lab frame, high energy hadronic interaction model will take care of that. And if it goes down below that, then low energy hadronic interaction model will take care of that. And the simulation parameters are: the primary particle is the proton. The primary energy range is 18 to 19.2 10 to the power electron volt. And spectral index is -2.7. Zenith angle is 20 degrees. And observation level is the sea level. And the first interaction of this primary particle is 1 kilometer above the sea level. So just 1 kilometer above the sea level, I've taken as the first point of the interaction of this cosmic ray. Now, in order to take care of the charm production in this Corsica, the Sybil model, by default, it produces explicitly the charm particles, but we can switch it and switch it off, on and off, by using this SIP CHM keyword in the data card, input steering card, by keeping it true and false. And there's another option, this is called charm. We can do the decay plus propagation both of this charm particle, or if you want, we can just say that okay, they will not decay, but they will not be propagated, but they will decay at the point of interaction. If you want propagation, then we can also switch it on using this charm option. So we generated the events using this charm selected, that is, we want both the decay and the propagation of this charm particles. And we alternatively switched on and switched off this charm production in this Corsica. So we divided this energy bin into 6 logarithmic energy bins of intervals 0.2, as you can see in this table. So 10, we generated like 100 events in the first bin, 46 and 20, and like that up to last 2 events in the last bin. Because when you go towards the last bin, the secondaries are so huge that the storage is data file that comes at the end is very large, and it takes much of computation time. And since we have this workstation, we limited resources for doing that. That's why we just kept it very low. But we generated equal events in the case of both charm on and charm off. So for example, in the first bin, 100 events for the charm on and 100 events for the charm off. Okay, so this is the energy distribution of D mesons. As I said earlier, that even if the production of these charm mesons are very small, you expect that these mesons are produced at PV energies, as you can see here in this histogram. So most of the mesons are PV energies and above. And this is the energy distribution of the muons. As you can see, with charm, we have an enhancement in the muon count above 100 TeV. And without charm, it's less enhanced. Okay, this is the momenta. Again, the same thing, the enhancement at the above 100 GeV per C, and with charm and without charm. There is a little bump there that is due to, because this is the transverse momenta that we are talking about. Transverse momenta means at a particular plane and along the shower axis, transverse to the shower axis, we are seeing how many counts of momenta is there. So since this is a muon, so imagine a cone around the shower axis, and in a particular radii of that cone, you will find most of the muons, and after that they got decreased. Okay, this is for neutrinos. So it's not a particular flavor, but all the flavors are combined: electron, nu e, nu mu, and nu tau. All the flavors combined. Again, you can see when we consider the charm production, this is an enhancement after 100 TeV. Without charm, it's not there. Similarly, for the momenta, when you consider the momenta of these neutrinos, we see an enhancement in the charm side, and not an enhancement in the without charm side. So, and when we consider the electromagnetic components, you see there's not much of a difference when we have this with the charm and without charm, because you saw earlier that most of the mesons decays to muons and neutrinos. So there you will see the more enhancement, not in this case of the electromagnetic components. So this is the case for the electromagnetic component, combining both the electrons and both the photons. Similarly, in the case of the electron and photon momentum, there's no enhancement with and without charm. Okay, to summarize, so we just have done a very basic study of the Corsica simulation considering ultra high energy protons, and we studied the ES content of these electromagnetic components, muons and neutrinos, and we found that there is an enhancement if we consider the charm option on and charm option and without charm. So the next thing that we like to go upon is that since we considered only the proton, and you know that the proton are not the only cosmic rays that comes in, so we'll include other primary particles like helium, nitrogen, and aluminium. We considered only one hadronic interaction model, which is Sybil. So we'll now consider other hadronic interaction models also. One thing that is there in the, if you remember the simulation parameters, the spectral index was -2.7. But if you consider, if you remember the energy bin starts from 18 to 19.2. So you might ask, okay, there is a break in the spectrum around 3 eeV. So above that is 3.1, and after that it's like 2.6. So maybe we can do a break in the spectrum and try to do this simulation again. And if possible, if time permits, then we'll include some other decay channels of this charm plot to see what happens. So yeah, thank you.
So these distribution that you showed, this was assuming a certain flux and observation time with grapes, or I mean, you had like these count maps there?
No, yeah, I mean, this is just a pure simulation. I mean, we didn't consider any time. Yeah.
Okay, so this would be also the next step to see how you observe this then in grapes in terms of event signatures. Okay. So unfortunately, we have to move on because we like 50% of the people want to go on an excursion later today. So let's thank Bhanu again.
Okay.